안녕하세요. 삼성 SDS 연구소 AI 연구센터장 권영준입니다. 이번 테크토닉의 키노트 연사는 프로그래밍 언어학 분야의 저명한 컴퓨터 사이언티스트이신 그렉 모리셋 코넬 테크 부총장을 모셨습니다. 그렉 부총장의 키노트 제목은 The Future for Software Security입니다. 그럼 그렉 부총장을 연결해 보겠습니다. Hi, Greg. How are you?
Good. How are you?
How's the weather in New York?
It's a little cool, but doing okay. Thanks.
It's getting colder here as well. On behalf of Samsung SDS, I'd like to thank you for giving us the Techtonic 2021 keynote speech. 그러면 지금부터 키노트 강연을 시작해 보겠습니다. Greg, shall we begin?
Please, thank you so much. I'm privileged and honored to get a chance to speak with you all today. I wanted to talk a little bit about where I see the future for software security going, at least part of it. And I can start with this slide here that just details some headlines from around the world. It seems like almost every day we're hit with another headline about some major breach in some major system around the world. And the situation just seems to be getting worse and worse. In fact, we can see from this graph, which I borrowed from another presentation, that indeed that's the case. If we look at the lines of code that go into producing a piece of malware today, or in fact, over the last 20 years, it's about constant. It's about the same size as it was back in 1987 when Robert Morris Jr. launched the original internet worm. In contrast, the defensive software that we're deploying, for example, unified threat management or network flight recorders or other things, firewalls, et cetera, the size of that code keeps increasing exponentially. So it seems that the defenders are actually at a huge disadvantage compared to the attackers, at least in terms of the effort it takes to produce the code for defense versus attack. And in fact, the situation is much worse than this graph makes it appear, because often the code that we used for security just runs in the context of for example, a kernel or a system that just increases the security footprint, the vulnerability footprint of the software itself. So all those extra lines of code just introduce more and more challenges for vendors and operators. Now, of course, with security, there are many things that are hard and are broken, not least of which is the interface with the users. I mean, if we think about it, passwords and phishing attacks are some of the biggest problems that we face today. It's not the only thing, though. I mean, the underlying architecture that makes up systems is often just flawed. For example, we often don't have data that are encrypted at rest. Our organizations make it hard to do an audit. And we often have a mismatch of abstractions. For example, the hardware on which we're running, we like to pretend like it's sequential instead of parallel or speculative. And that leads to attacks like Spectre or Rowhammer that allow attackers to subvert the abstractions that we depend upon. And of course, in the cloud, everybody knows that one of the biggest challenges is just the configuration and the operation of the myriad systems that we're trying to coordinate in an application today. But even though these are all stunning challenges for security operators and researchers, one issue still continues to dominate most of the vulnerabilities that attackers take advantage of. And that's that, frankly, the code that we write, the systems level code, for example, the operating systems, the network devices, the databases, all of these are full of bugs that attackers can take advantage of. So there are a number of things that are going wrong in the production of that system software that is frankly ineffective. One challenge is that today we rely on humans to review the code and look for flaws in that system's code. But humans aren't very good at this. They're not patient enough to actually work through all the details and all the paths to make sure that there's not a vulnerability lurking in there somewhere. People have turned to analysis tools, static analysis tools or dynamic analysis tools to try to find the bugs that are lurking after a human-led review. And these analysis tools, the static ones, tend to trigger way too many false positives, and the dynamic ones don't do the coverage that we need in order to uncover everything. So they're incomplete or unsound. Another challenge is that the certification processes that are used, for example, by the military or by government agencies when they're trying to produce highly secure software, are ineffective. They're often based not on the code itself, but on who authored the code. Where did the code come from? And that subverts the whole idea of open source. We don't care where open source software comes from. We just care what it actually does. And I worry that as we rely upon the provenance of the code, where did it pass through, instead of what is the code actually doing when we execute it, we could subvert the process of open source overall. And another issue is that the automated defenses that we're deploying are often really bad. For example, there was a good New York Times article just the other week recommending that you shouldn't run a virus scanner on your laptop or PC, and for good reason. They're actually pretty ineffective. But it's worse than that. As I said before, they often run in the context of the kernel with privileges, and they have bugs in them that just give another foothold for the attacker. The biggest reason these tools, whether they're intrusion detection tools or firewall tools, et cetera, that are scanning packets aren't effective, is that they're looking at some syntax of things, not the semantics of things. And that's the fundamental challenge that we face in software security. If we had our way, what would we build and what would we put together if we're building a new cloud system? Every bit of code that we bring in and we import should ideally pass through some inspector, and that inspector should check the code to make sure that no matter what paths we execute, there's not a flaw in the code that can lead to a vulnerability that an attacker can leverage. And so we need to write down some kind of formal security policy and have the inspector check the code against that policy. And importantly, the inspector shouldn't be looking at the syntax of the code, but thinking about the behaviors of the code when it's actually executing. And ideally, that inspector should be simple and small and very trustworthy. If it's not, if it's a big, complicated piece of code, then we may just introduce more bugs into the system. Unfortunately, the idea of that inspector, that magic inspector, is just that, it's magic. Almost any interesting security policy is wildly undecidable. So looking at the code and trying to decide, will it violate a security policy when executed, is hopelessly intractable no matter what you're trying to do. And that's the challenge with static analyses, is that at the end of the day, they're trying to prove something that's really hard, and constructing that proof is usually intractable. But there is a way out of this mess, and it's an old idea. It goes back to the late 90s with people like George Nekula and Peter Lee. And the idea is pretty simple. The idea is, instead of requiring the inspector to come up with some sort of evidence that a piece of code respects a given security policy, instead, what we should do is require the producers of the code, whoever's writing the code to begin with, to come up with a proof that can be checked by the inspector. And the insight here is that finding proofs is incredibly hard, intractable in general, but checking proofs can be very easy, and it can be automated. So the inspector can be a simple, small, trustworthy piece of code that looks at a combination of the new software that we're trying to load into the system, together with the proof that that code respects the given policy. This is the idea behind proof-carrying code. As I said, that's an old idea that dates back to the 90s at least. And it's a really interesting architecture to try to explore in the context of modern systems. So the idea behind formal methods or machine checkable proofs enables a whole lot of things. First of all, we can cover all execution paths in the code with a proof. And the way we're doing that is through symbolic reasoning. In fact, we can cover infinite paths, loops, and this sort of thing through the code in ways that model checking often can't do, or static analyses are too conservative about. So proofs enable us to reason about the code end to end. They also make it easier to modify the code with confidence. Often we want to introduce an optimization, or we want to make a change, introduce some new piece of software. If we can do that and we can still respect the parameters of the proof, then we can do so with confidence. Often today, when we make a change to the code, we have no idea what we're going to break because we really don't understand what's in the code. And finally, as I suggested earlier, this could be an architecture that can support open source code development because we don't care who produced the code or the proof. All we care is that the code actually respects or has a proof that it respects the given policy. Actually, this idea of proof carrying code really dates back well before the 90s to people like Dijkstra and Hoare, the sort of pioneers of formal verification back in the day. It's a really old idea, but of course, most people think it's unworkable. I mean, after all, this architecture still requires somebody to come up with a proof. In this case, it's the code producer, and coming up with proofs is pretty hard. So what's changed in the last 10 years or so that enables this to happen? Well, first of all, there are new languages, frameworks, and logics for reasoning about real code. So that includes systems like Coq and Agda, F-Star out of Microsoft, Isabelle, and so forth. These are all proof development environments that allow people to reason about big systems in tractable ways. Another thing that's happened over the last decade or so is the introduction of new kinds of program logics, like concurrent separation logic, that are powerful enough to reason modularly about real software and real systems. Another thing that's happened over the last few decades, or last 20 years or so, is models of real systems. And by real systems, I mean, for example, machines like the x86 or the ARM, and programming languages like C or JavaScript. We now have formal descriptions of the semantics of these systems. And so we can start to reason about code execution in the context of those systems. And finally, perhaps most importantly, over the last 20 years, we've seen dramatic improvements in automated theorem proving, including SAT solvers and SMT, or satisfiability modulo theory solvers. They've brought around multiple orders of magnitude improvement over the last 20 years. To give you an idea of the improvement, here's a graph from the SAT competition back in 2009. And this graph plots different systems over time trying to solve problems. And if you look at, say, the number of problems solved at that 80 or so there, and you just draw a straight line upwards, what you can see is that the more recent systems, like the 2009, 2010 systems, we're doing 2 orders of magnitude more problems in this, or reducing the time by 2 orders of magnitude to solve the same number of problems. So the improvements in SAT and SMT provers make it possible to knock off more and more automation in the theorem proving process around software. It's not the case, that just those things alone are enough. People have been building real systems and proving the correctness or the security of those systems in context. So I give you a few examples here. One is the amazing CompCert compiler that came out of INRIA. This started in 2006. Today, it's a full ANSI C compiler that targets a number of backends, including the x86 and the ARM. And the compiler is proven correct end to end. It's a mildly optimizing compiler, so it's not as wonderful as LLVM or GCC in terms of -03 optimization, but it implements a number of key optimizations. It produces relatively high performance code, and you get a theorem out at the end of the day that says the behavior of the target code that comes out is a refinement of the behavior of the source code. That's a pretty amazing accomplishment. Another good example of a real system is the amazing SEL4 microkernel out of Australia. So this is a full microkernel operating system that has been proven correct. That is, there's a behavioral model of the intended behavior of the operating system and a proof that the actual code that's running on the machine respects that behavior. In fact, from that proof, the authors were able to go on and prove other properties, for example, an isolation property, a strong isolation property about processes. So with compilers and operating systems, you get to see the sense that people are actually reasoning about and building real systems. Another example is Microsoft is building a new SSL stack end-to-end rewrite to make sure that the cryptography in their secure sockets layer is actually correct. And they're actually comparing that against the foundational proofs that cryptographers are actually pulling together. This helps to avoid, first of all kinds of challenges in the assumptions that cryptographers make, but it also avoids issues in the differences between the high-level models that a cryptographer might have and the actual code that's running on the system. For example, we saw a bad instance of this in the Heartbleed vulnerability that was a few years back in the OpenSSL stack, and that really prompted Microsoft to build a whole new fresh crypto stack. Another great example of formal methods at work in real systems is Amazon's Access Analyzer. This is a network access analyzer that takes advantage of an SMT prover to make sure that no one who shouldn't have access to a system or a component does have. And it's been amazingly useful within Amazon. In fact, Byron Cook leads a whole team at Amazon focused on formalizing different components of their cloud infrastructure now. And finally, it's not just software that we're able to reason about formally these days. A good example is the Kami project out of MIT, led by Adam Chipala and others, where they're reasoning about hardware that's being synthesized. And they're able to take on the kinds of challenges like the Spectre mitigation problems that we're having now with the x86. So these give you some examples of real systems that are at least in the research stage and are starting to transition to the real world. Let me give you one more, I think, really compelling example of a formally verified system end-to-end. This was a project that came out of DARPA a few years ago called HACMS, or High Assurance Cyber Military Systems. And the project was to take a drone, in fact, two drones. One was this little drone here on the left, which is a little quadcopter that you can buy in just about any store. And the other was an actual drone, military drone, a full-scale military drone. And what HACMS did was brought together a team of people to build a clean slate stack. They started with SEL4 as the microkernel and built their way up, including all the things you see here: stability control, attitude control, direction, and so forth, and navigation. And they encapsulated third-party software inside of containers that were proved to be secure. They proved that the system was memory safe, that it ignores all malformed messages coming from a controller, that it ignores non-authenticated messages, and a liveness property that all good messages will eventually reach the controller. So end-to-end, they were able to prove a number of key safety and security properties about that whole stack that runs on those systems. So how good was this in a security context? Well, the DARPA folks decided to hire a team of really good hackers, and they gave them access to the source code for 6 weeks. This was a red team within the Department of Defense in the US that were good at breaking systems. And even though they were given the source code in a full 6 weeks, they were unable to break it. Later on, in fact, just recently, DARPA took that system to DEF CON and made it available to all the hackers there. And no one at DEF CON was able to break it. So that's not perfect. I'm sure there are still challenges in the things that weren't modeled, the things that weren't proven correct. But nevertheless, it shows that when you go this far, you can actually get very high assurance code. In fact, Amazon has really jumped on this in a big way. So this is Werner Vogels, who used to be a researcher at Cornell, so I thought I would flash his picture up, but he's now the CTO at Amazon. And he, in a recent keynote speech himself, talked about formal verification and the role that it plays within Amazon, not just for the analyzer that I mentioned earlier, but in other key things from their cryptography stack to their container technology. So I don't want to leave the audience here with the idea that this is just magic and that you can pull it out and use it today. There's still a lot of hard challenges in using the idea behind proofs and formal methods in the context of real systems, particularly cloud systems that we're seeing deployed at places like Samsung and elsewhere. So I'm going to walk through some of these challenges and try to point to some of the security properties that and security research challenges that I see going forward. So probably the biggest is actually formalizing the security policies themselves. For example, I've done a whole lot of work formalizing and reasoning about cryptography. For example, one of my students actually proved the correctness of a database encryption technique that allows you to do queries against the encrypted data. And this used some pretty modern cryptography. And what we found is that the paper and pencil assumptions that cryptographers make are actually relatively informal. And different cryptographers mix different assumptions. When you actually sit down and write a formal model of these things, it's actually a lot harder, but surprisingly useful, because then all the assumptions come together and people can understand what you're actually trying to prove. Another challenge is just defining what we mean by security in the context of a cloud application, or even something like a web browser. What does it mean for a web browser to be secure? We have things like the same origin policy, but more generally, there's a whole rich class of policies that a given system needs to respect, and formalizing those can be a lot of work. In fact, often that can be just as hard as writing the software itself. And finally, in the age of machine learning, what does it mean to put together a security or a safety policy around machine learning-based systems? That's an emerging research challenge that everybody's looking into these days. Another issue is constructing and validating environment models. For example, modeling the CPU on which we're running, or the network card, or the firewall, things that are beyond your ability to actually redress or take a clean slate approach on. And that's a big challenge right there. I mean, even something as complicated as an x86 CPU is incredibly hard to model. Again, one of my students, or a team of my students, actually spent many months trying to construct a model just for the integer portion of the x86 that was actually something that could be tested and put up against Intel's actual hardware. And of course, they have bugs in their systems. Everybody has bugs in their implementations. How do you model those or steer applications away from those particular failures or bugs? Another question is, how do we test these models? So we always have environmental assumptions in any formal methodology. When we construct these models, how do we test them against the real world? How do we validate those models? That's a big challenge for many systems. For example, in the CompCert compiler, there's a semantics given for both the source level of the C code as well as the semantics of the, say, x86 code that we're targeting. And how do we validate those models? I mean, for example, the C semantics is compared against the ANSI C standard, but that's just a pile of English statements. It's not very formal at all. Another issue is, when we're modeling systems, what level of abstraction do we use to model them? For example, in CPUs, we typically just model the instruction set architecture, that is executing one instruction after another in a sequential fashion. But we've seen with the rise of microarchitecture attacks like Spectre that we actually need to model things at a much lower level if we're going to catch those kinds of speculation or confidentiality attacks that arise from speculation. So that's another big challenge for formal methods these days. Another challenge is that we really need more research on automated theorem proving. It took the authors of SEL4 back in the day 20 person years to actually prove that their operating system was secure. That's a lot of effort. Now, the good news is that more recent efforts, like the Certicos operating system out of Yale, was proven correct in about 20 person man months instead of 20 person years. And so we've had big improvements due to a combination of higher level abstractions and reasoning together with automation in the proofs. But one of the challenges is that right now that SMT provers really only handle largely quantifier-free fragment of first order logic. And usually when we want to model these things, we want to use fancy new higher order logics, for example, like that concurrent separation logic that I mentioned earlier. And we need new techniques to actually provide automation in those higher level logics. Another challenge is, if you look at these SAT and SMT provers, they're largely not taking advantage of parallelism. They're largely still using sequential machines. And I think there's a big opportunity to take advantage of cluster scale compute to do theorem proving in a modern way. Another interesting question, research question is, can machine learning be applied to synthesizing proofs? We've already seen machine learning applied to synthesizing some software, some code, but we haven't seen it yet effectively synthesizing proofs. And maybe it can help us out in this critical domain. Another challenge is re-architecting systems to reduce the proof burden. For example, in the CompCert compiler, instead of proving that the graph coloring register allocator was correct, what the authors did was actually used an untrusted graph coloring algorithm, but they checked afterwards that the coloring was correct. And that's back to that basic principle that often finding a solution can be very hard, but checking a solution can be easy. And you only have to prove the correctness of the checker, not of that finder, if you will. So finding architectures like that that lower the proof burden are important if we're going to apply this in the real world. Another challenge is finding abstractions that are compositional in our reasoning. Certicos is a great example of that, and I mentioned it earlier. This is work of Zheng Xiao out of Yale. He was able to find a set of new abstractions for proving refinements around operating systems that allowed him to scale that development and prove things much more quickly than, for example, the SEL4 folks did. And finally, we need reusable libraries and models so that we're not having to prove things for the first time all over again. There was, in fact, a big NSF project, National Science Foundation project, focused around this, headed by people like Andrew Appel at Princeton and Benjamin Pierce at the University of Pennsylvania. Finally, perhaps the most important thing is training, that we really need to build a new cadre of not just software engineers, but what I would call proof engineers, people that know how to write software and construct and maintain the proof that the code is correct or secure. And few universities around the world are teaching this well today. It's a new emerging domain, but something that I think we'll be seeing much more of over the next decade and beyond. In fact, I would argue that we have an emerging field of proof engineering that's just as vital and perhaps just as important as the field of software engineering. So there are many challenges that we face in using formal methods going forward. But I think these are interesting and challenging research problems that can be tackled. Getting back to it, though, formal methods will only help with those bugs in the software systems. We still have these other hard challenges in security, including users and user interfaces, the underlying architectures of systems, the mismatches of abstractions, and of course, the configuration and operation. But formal methods can help with many of these things as well. For example, Amazon is using formal methods to help with their configuration in their network architectures. So I think this is a new and emerging area for system software. It's really formal methods, people meeting system software in the middle. So that's what I had to say, and I hope you appreciate that. I'm happy to take any questions that folks have.
Thank you for inspiring, yet technically insightful presentation, Greg. Samsung SDS is a software company, and at the heart of it, there are many talented software developers who spend most of the day writing code. We have software production process that enforces a part of what you have said today. Our process is largely empirical, need-oriented, rule-based. How can you embrace the presented methodologies into our software engineering practice? Perhaps, do you happen to know best practice examples from industry?
Great question. Yeah, I think a couple of the leaders in industry are, for example, Microsoft and Amazon have formal methods teams that have been going after particular stacks. For example, I mentioned Microsoft has this OpenSSL stack that they're re-architecting from the ground up. And I think what you learn is, first of all, using the tools that Samsung is already using is really important. You don't want to try to prove code correct if it already has easy to find bugs with static analysis tools or fuzz testers, but you want to use those first. Then you want to sit down and write down as much of a specification as you possibly can for what the intended behavior is of the code. And often that uncovers big challenges right there without actually doing a formal proof. You often get a lot of the benefit just from writing a specification. And then finally, you want to use modern logics and tools. For example, the VST logic that Andrew Appel has put together makes it possible to reason about high-level C code using something like concurrent separation logic. And if you pull all those pieces together, then you can start to reason about things. But it's important to take advantage of that architectural design that I mentioned earlier that allows you to try to minimize what you're reasoning about formally. Ideally, it's a small, simple core that encapsulates the critical security functionality.
Thank you. I lead AI research at Samsung SDS. Do you have any suggestions or things to say about AI and software security, perhaps?
Oh, yeah, quite a bit. I mean, I think this is the hottest area of research these days, in part because there are new kinds of attacks brought on by the rise of machine learning, from data poisoning attacks where attackers feed you bad data to throw the models off, or model extraction attacks where attackers use queries to reverse engineer a model, to privacy attacks where attackers use the sort of overfitting that the typical models do today, the deep learning models do today with so many parameters, to extract information about individual training data that's used to build up the model. So those are some of the challenges that I think we face. And it's interesting that technologies like differential privacy, when used in the training of the model, can actually help not only with the security and privacy challenges, but also with these overfitting issues that people have. But maybe that's an approach. I think another thing that I'm excited about is just using machine learning for more security challenges. So I mentioned, for example, proof synthesis or code synthesis. I think one challenge right now is people are trying to synthesize code from Stack Overflow, but we know that Stack Overflow code is full of bugs, right? So that's a bad idea. But doing something like proof synthesis would be a really good idea. A lot of people are trying it on intrusion detection, and I haven't seen good results yet. So that'll be an interesting thing to watch, whether machine learning models could actually be effective in that context.
Okay. Lastly, Greg, to our promising young software engineers who look up people like you, do you have any final message as a renowned computer scientist, an educator, and a university executive?
Oh, great question. I guess never stop learning. The world keeps changing out from under you. I mean, it's only been a decade ago that machine learning revolutionized the computing world, really deep learning, I should say. And it was really something that's been around for more than 50 years, but it really was a confluence of some algorithmic changes, a lot of data, and some clever people pulling it all together, and new compute platforms like GPUs coming along. So I think never stop learning, never stop being curious, and never give up on what you know is right in the long run.
Greg, thank you very much for your time today. I should now say goodbye to you, but I'll be in touch. So long, Greg.
Thank you so much, and thanks for having me.
이상으로 텍토닉 2021 키노트 강연을 마치겠습니다. 감사합니다.